Okay, so today the quiz will start at 3:15, and it will just automatically come up on Blackboard. And so I'm going to lecture until 3:15, and then the quiz will come up. So you have basically 30 minutes for the quiz. You actually have 35 minutes. I mean, it depends when you want to leave class. Uh, I try to stop class about 15 minutes before 4 because that's the standard thing we do around here to give you enough time to get to your next class, which can be all the way across campus. But the quiz is going to go off at 3:45. So it will start at 3:15. It will suddenly go away at 3:45. Yes. You won't need a calculator. Um, now, I if you look at Blackboard, you'll see that I changed the agenda. So down here, this no longer says agenda, it says revised agenda. And if you open it up, it's a little bit different from before. It reflects the fact that this is what I've actually covered up to this point. And so basically, some things have been sort of moved down a little bit. So we see here on the week of 9/25, we're still doing hardware. So I've expanded how long it takes to cover digital technology and hardware. And so since I'm going to leave it that way, for the future. And then I've got A1 due this week here, 9/25. Instead of the previous agenda, it was due on the 18th. And I've got A2, which is going to be handed out, not this week, but next week. Also, A2 is going to be having to do with presentation software, that is, with PowerPoint. And A3 is going to have to do with spreadsheets. I've changed them. The reason I changed them is that I want you to give little 5-minute talks, okay, on your presentation. And so I need you to finish that earlier in the semester. So look that over, okay, to get used to the change in the. Anybody have any questions about that? So you can look at it, okay? All right, so I'm still talking about hardware, and so last time we got down to talking about the motherboard and the buses, okay? And then the machine cycle, okay? Now I want to talk about the machine cycle a little bit more. Mr. Christopher Valverde, how you doing? Good. So I want to talk about machine cycle, okay? And What? Just I don't know. So I want to talk about machine cycle. I'll tell you what, I'll make a deal with you. I'll speak a little louder if you'll speak a little softer. Is that okay? So what we have, I want to talk about how a machine works. And each computer has what's called an instruction repertoire. That is, it has a certain set of things that it can do. And these things are programmed into the hardware of the computer. And so when you write a program for the computer, ultimately it has to be a list of these things. So for instance, one thing that a computer has to do is it has to input data. And so there will be an instruction like input. And this instruction will have certain addresses. Okay, they go with it, and it'll have something like an address and a link. Okay, Nat Bowie, uh, Nat Bowie, how you doing? What is the last thing I just said? So an instruction has uh, an instruction, and it also has operands. Okay, so this input instruction might have a couple of operands. Okay, the first operand might be an address. Operands. These two things here are operands. That is, these are things that are being operated on. Okay, this address is one of the addresses in primary memory, and this length is a number. Okay, an integer. Okay, except the length might be stored in 1 byte. Okay, this address here is going to take several bytes to store. Right. To put so basically, what you're going to do is you're going to put data into the computer. Okay. Store means to put data into the computer. Okay? And basically, the input says input. Okay, so think of the input as simply saying type on the keyboard. Okay, it's an instruction to the computer, but it's also it causes the computer to wait for the person sitting at the keyboard to put stuff in on the keyboard. Okay, and as the person is typing stuff on the keyboard, it starts typing this stuff into the address listed in this instruction. And the number of characters that it takes is given by a length. Okay. So if we say input to address a 100, okay, 3, okay, then into address 100 in memory, we're going to take 3 characters. Okay. So the first character that the person types will go into address 100. The next one will be in 101, and the third one into 102. Now these addresses are always in hex. This will be a decimal address of 256. Then the computer will have some sort of output instruction. And it'll have an address and link. And this will output information from the memory, starting at that address, okay? And it'll output that many characters. The output will be on what's called the standard output, which would normally be, say, your screen. Okay? So the input would come from the keyboard, the output would go to the screen. There will then be some sort of instruction, such as load, and it will have an address, and then it will have a register. The CPU has registers, okay? So basically, you've got your CPU up here, you've got your memory down here, it's primary memory. This primary memory has addresses and contents. The addresses start at 0, 1, 2, 3. The addresses are in hex, okay? Addresses are 4 bytes long. And the contents are 1 byte long. Okay? CPU will have registers. And each of these registers will be 32 bits long. And it'll have a register 0 and a register 1, register 2. Normally 16 registers up to R15. And each of these registers is 32 bits long. It's just more memory. However, it's very fast memory. And it has extra circuitry involved in it, as we'll see. So if you wanted to, say, read in 2 integers and then add them together and then print out the result, okay, the program would look something like this, okay. Let's call the first integer A and the second integer B, and we're going to add A to B, and that's going to give us the result C, okay. Now, when you write a computer program, it's done pretty much in algebra. Algebra is for reckoning with letters. Okay? In German, the word for algebra basically is in German letter reckoning. The reason the programming is done in algebra is because you don't know what these values are. You're writing a program to add a number, which is abstractly called A, to another number B, and to get a result C. Okay? Once you write this program, it doesn't matter what the numbers are. Okay? You'll read in some number, A. You'll read in some number, B. You'll add those numbers together, that will produce an answer, C. So what we think of in computer programming, we think of these letters, A, B, and C, as being memory addresses. Okay? So the computer program to do this would look like something like the following. It will say input A, that's an address, okay? And then we're going to say how long A is going to be, okay? Now here, it can be one character long, 2 characters long, 3 characters long, okay? It can be up to about 9 characters long because we have a limit in storing integers of about 2 billion, right? So let's say A is 3 characters long. Okay. Then we'll say input B, and let's say B is 4 characters long. Okay. Then the next instruction will be something like convert ASCII to integer. Okay. A 3 into, say, register 0. Convert ASCII to integer B 4 and put that in R1. Okay. So this register R0 in the CPU is now an integer data type. It's 32 bits long. And this convert ASCII to integer instruction has converted the 3 ASCII characters that were typed in for A and converted it into an integer. Similar for B. Then there might be an instruction called add, which adds integers, and it adds R0 to R1 and puts the result in R2. We then will have a convert integer to ASCII, and that will be C, okay? C will be at most, say 5, okay? R2. This will take the integer, which is stored in R2, okay, convert it into ASCII, a maximum of 5 characters, okay? And then we will output C. Okay. That's what the program looks like, okay? Now, this program is stored in memory. And so let's say this program is stored at memory location 1000. Well, each one of these instructions, just the instruction part, will be 1 byte, okay? And anything that's an address is going to be 4 bytes. And anything that's a length or a register is going to be 1 byte. So this first instruction basically takes up 6 bytes of memory, which would be 1000 up to 005. This next instruction starts at 1006. Okay, it's also 6 bytes. Okay, so the next one is going to be at 12. Okay, and this one is going to be 1 byte plus 4 plus 1 plus 1. So it's going to be 7 bytes. Okay. So that's then going to be 1019, okay? And then the next one is going to be 7 more bytes, okay? And that would be 19 and 7 be 26, okay? okay, and so forth, okay? So that would be what a program would look like in the computer. Now, the way the machine cycle works is there is in the CPU something called an instruction counter. And this instruction counter here will be set to a certain memory address. And somehow to run this particular program here, there has to be some program that sets the instruction counter to 1000, okay? And that would be the operating system, right? The operating system wants to run your program. It will basically load your program into memory somewhere, and then it will set this instruction counter to where your program begins, and then basically it will just let the CPU run your instruction, your program. Now, the CPU will start at this location in memory. The first part of the memory cycle will be to fetch your instruction. So the CPU will fetch this byte here, and it will look at this byte and say this is an input instruction. It will say the input instruction is 6 bytes long. It has 2 operands, an address and a length. So it will then increment this instruction counter to 1001, pick up the first byte of this address, and then 1002, and the second byte, the third, you pick up all 4 bytes of that. Then it will pick up this one by here, and then the instruction counter will then now be setting at this address here. After fetching the instruction, the second part of the instruction cycle kicks in. The second part is the decoding part. And it says it has to decode. What is this instruction? It's telling me that this program wants to input data from the keyboard. It wants to have 3 numbers input from the keyboard. That causes the circuitry of the computer to just set up and wait, okay, and not do anything until the user types in 3 numbers from the keyboard. Now it's expecting numbers, and it's expecting the user to type in a 0, a 1, a 2, up to a 9. It's not expecting the user to type in an A or a Q or something like that, which of course the user might do. Okay? But assuming the user types in something proper like 685, the user will type in a 6 and an 8 and a 5. Okay. The 6 will go into address A in memory. The 8 will go into A plus 1. Okay. The 5 will go into A plus 2. Okay. It has now executed the instruction. Okay. So it's finished. Okay. It now starts a new instruction cycle. Okay. It fetches this instruction. Okay. It then decodes that instruction. It then executes that instruction. Okay. Here it is expecting it to the user to type in 4 characters on the keyboard. Then it comes to the next one. Okay. The next one says convert ASCII to integer. So the CPU fetches this instruction. It knows the convert ASCII to integer requires 3 operands: an address, okay, length, and a register. And so the CPU goes to the memory, fetches A plus 1, and A plus 2, okay, the 3, and converts them into an integer and stores it in register 0, which is a register in the CPU that has 4 bytes. It then goes to the next instruction, does the same thing. It then executes an add, register 1 to register 2, register 0 to register 1, put it in register 2. Okay? This is all integer data types. Okay? The integer stored in R0 is added to the integer stored in register 1, and the result is put in register 2. This does a convert integer to ASCII, okay? And it converts R2 into 5 ASCII characters stored in address C. Yes. Yes. 3 what? Yes, it says, hello, come in. This says convert ASCII to integer. The ASCII characters start at address A in memory. A will be a number, okay, somewhere in memory. And then it says there are 3 ASCII characters. Okay, so the first one is at address A. The second one is at address A plus 1. The third one is at A plus 2. Okay? So this will actually get all 3 ASCII characters out of memory, and we'll consider the 3 as being a 3-digit number. It'll be a decimal again, and it converts it, okay, into a binary integer and stores that binary integer in the CPU in register 0. It then converts 4 ASCII characters starting at address B and makes an integer out of that and puts it into R1. It then adds the integer that's in R0 to the integer that's in R1 and puts the result in R2. This addition is done in something called the arithmetic logic unit, or the ALU. This then converts integer to ASCII. And it takes the integer that's in R2, converts it into 5 ASCII characters, okay, starting at address C. So once this is finished, at address C will be a character. That'll be the lead character. C plus 1, C plus 2, C plus 3, and C plus 4 will be C, okay? And then it'll output those 5 characters, okay, on the screen. Yes? Mm-hmm. Those numbers are the addresses of the instructions of the program. This 100 is the address of this instruction here. Okay? This instruction is in memory address 100. The input itself, the input instruction is in memory address 1000. This address is in 1001, 1002, 1003, and 1004. This 3 is in 1005. The next instruction starts at 1006. This input is in address, the input instruction, and this input instruction is actually coded as some ASCII, some binary value. Okay. This input instruction here is in 1006. This address of B is in 1007, 1008, 1009, and 1008. The 4 is in 1, 0, 6, 7, 8, 9, 8. Okay. B. Oops, I'm off. So this is a C here. 6 plus 6 is 12, and a 12 in hex is a C. Sorry. So this is going to be a 4 and a B. So this next instruction here, the CAI, convert ASCII to integer, will be in memory address 100C. This address will be 100D, 100E, 100F, and then 1010 again. This will be in 1011. This will be in 1012. This will be in 1013. Well, I guess I had that right. So this will be in 1013, 14, 15, 16, 17, 18, 19, 110. This is 18. So these numbers out here are, so in the memory, you have both the data and the program. And the program takes that memory just like the data. That's one of the real advantages of computing. That was one of the big ideas originally when computers came out, is that you can store the instructions on what to do in the same memory that you store the data that it works on. And in fact, you can even have the program work on itself. That really makes the computer very powerful. Okay, so that's the way then computers work. So basically, this machine cycle, each instruction goes through this 4-step machine cycle. The computer has to fetch the instruction. The instruction will be in several bytes, as we've seen here in this little example of mine. Each instruction takes up 6 bytes of memory, or 7. So it has to fetch those 6 or 7 bytes, has to decode them, it then has to execute them, and then it has to store any result. Then it goes to the next instruction, okay? Okay, so we've looked at RAM storage, random access memory. That's your main memory, okay, is random access. We've talked about video memory, okay? You'll have, in most computers nowadays, you'll have a video card, and that will have extra memory on it, okay? But that memory is just like part of the main memory, and certain addresses have been reserved for the video card. Read-only memory, I talked about that last time. It's the memory where you store your boot-up program or your BIOS, okay? BIOS is a basic input-output system, okay? And that's the first instruction that the computer runs when you turn it on. Okay, I'm going to talk about magnetic storage, optical storage. Random access memory looks like this. This is a card he holds. You go and you buy that, and if you have a computer and your computer's running a little bit slow because it doesn't have enough memory, you can go down to Fry's. You buy one of these little memory cards like he's holding for about $20, $30, depending on how much memory you want. And you open your computer up, and there'll be vacant memory slots. And you just take this memory and you just push it in there. Video memory, so there's a whole card for the video memory. And ROM, I mentioned that. Now, I want to talk about magnetic storage. If you have, a CD or a DVD or a Blu-ray disc, and all the discs are something like this, okay? The difference between a CD and a DVD and a Blu-ray disc is how densely the data is packed inside the disc, okay? And so here on a CD can hold about, I don't know if you read that or not, about 0.7 gigabytes of memory. Less than 1 gigabyte on a CD. On a CD, you can store things like music. You can store things like text, pictures, okay. A DVD, on the other hand, okay, will hold 4.7 gigabytes. So it's much more data on that disk. It's more densely packed, okay. So the way it works is this disk is spinning around, and as it spins around, these these various tracks, okay, are passing the read head. And this thing right here represents a place in the disk that's been burned out. That's a little hole, a little ditch, okay, in the disk, okay. And this here is a place where the little hole is not burned out again. And so if it's not burned out, it's a 0. If it's burned out, it's a 1. Yeah? And as the disk passes under there, okay, it's reading these 0s and 1s. Okay. Look at the DVD. The little holes, okay, are much shorter and much more tightly packed. In a Blu-ray, it's Blu-ray can hold about 25 gigabytes, okay, and very tightly packed. Okay. So there's solid state storage, okay, like you have on your camera. If you got a digital camera, you'll have a little solid state disk, okay, or with little flash drives. I've talked about cloud storage, okay, and that's where you store your data not on your own computer, but at somebody else's computer on the internet. Somebody that's offering cloud storage service. The advantage of a cloud service is you store it there. Then, I mean, if you use a bunch of different computers, one of the problems people have is that you've got a data on one computer and now you're using another computer, but the data you want is not on that computer. So if you store everything on the cloud, then it doesn't matter. All your computers that you use, any computer anywhere, you just get on the internet and that data is available to you on the cloud. So I/O, input general purpose I/O. An input device assists in capturing data into a computer. So you're all familiar with this, right? So this lady here is scanning something, right? And it's a barcode, right? You go buy groceries, got all this stuff in your basket, you got to pull it out one at a time and scan it, right? But now they have a radio frequency ID. Now, it hasn't gotten down to the grocery store level yet because it's a little too expensive. But in my opinion, the time will come when they won't have these barcodes. They will have these RFID stickers. Okay, RFID is a radio frequency ID. Those little bitty stickers are a radio. They're broadcasting. Can you imagine? It's a sticker, little radio. It's not broadcasting very much. Okay, but it's a little radio broadcast. Yeah, it is. It's too expensive right now. Okay. And they use them. They use them in warehouses. Okay, to store, product that costs a lot of money. But one of these days, I think they'll be cheap enough. So you go into the grocery store, you put all this stuff in your basket, okay, and then you'll just push your basket up to the counter. Some kind of reader, $100. You won't have to take all that stuff out. And it'll give you a list of everything. Okay, is it started yet? Oh, okay. As soon as the test starts, it's a one-time. Okay, once you start it, okay, it's going to force you to finish. Okay, and you won't have another chance on that test. Uh, the computer's going to try to grade your test, but you will not be able to completely grade it because the answers are, in some cases, individualized. Like it says, what is your age in binary? So the answer is going to be different, and the computer is going to try to grade that. Okay, but we have to check it over. Okay? So it's not a test that the computer can completely grade. Okay? Now, no talking. Okay, no talking during the quiz one. Yes.